And my plan is to give some kind of experience report about what a standard mathematician can do with Lean. So I started formalizing complex analysis when I was teaching an undergrad course on complex analysis, something 2-3 years ago. And I'm going to talk about what this led to. I'm very bad at attribution. I did not do everything that I'm going to present, and I will try to attribute the various results. And so my plan is I'm going to tell you about the Riemann mapping theorem as an example of some mainstream mathematics that is formalizable in Lean. So this is the statement. You take omega, which is a simply connected domain in the complex plane, which is not C. Then there is a conformal map, so biholomorphic bijection, between omega and the unit disk. That's one theorem. That's essentially the last theorem of this course I was teaching, and I was trying to formalize as I went. As you can guess, it did not go as fast as predicted, so I gave this course 3 times, and by now everything essentially is formalized. So here's the plan for the talk. First, I will give you a quick blackboard overview of the proof. So purely normal mathematical proof, just to have a framework of what we're going to do next. Then I'm going to show you a few bits as they are formalized in Lean and what I did here. And then I will reveal that I was cheating. So I'm not going to actually prove this theorem. I'm going to prove a different version with a slightly different hypothesis, and I will tell you what the main obstacle is. And then I will describe some work in progress about solutions to the problem. Okay, so all the code is in one repo of mine, and I will also talk about a different project as we go. But okay, so let's start. So how do you prove the Riemann mapping theorem? I will give you a quick outline of the proof, of the standard proof, and then we'll see how to formalize that. So we have omega, which is a simply connected domain, and we want to find a conformal map from omega to the unit disk. So what do we do? So this is the unit disk, and we want a conformal map from omega to the disk. So what we do is we look at the set of functions f that go from omega into the unit disk and which are holomorphic. So there are embeddings of omega in the unit disk. We fix a point z0 in omega, and what we do is we want to maximize.
You are talking about injected function.
Yeah, this is an injection into D. So we want to maximize the modulus of f prime of z0 for f in this big F, which is this set of functions. And the main argument is if you take a function that maximizes this, then automatically it is a holomorphic, it is a conformal map from omega to D. So this is the plan. So to give some detail and what is needed in terms of theoretical results about complex analysis, so there are 3 steps. So step 1 is you want to show that this collection F is non-empty. It's better if you want to take a maximum. So to do that, you want to give an explicit function that is an injection between omega and D. Okay, so let me give you a quick argument. So this is omega. Up to translation, you can assume that 0 is outside of omega. And so you get you have a holomorphic function on a simply connected domain. The function does not vanish. So this is the identity, and you can define a square root. So you can define square root of z that goes from omega to c as a holomorphic function. Okay, and this z is an injection, so square root of z is an injection, and it doesn't take two values that are w and minus w, because that would contradict that z is injective. So if w is in the image of square root of z, image, maybe im is not image of square root of z, then minus w is not in the image. Okay, so in particular, so square root of z is an open map. The image of an open set is an open set. It contains some ball of positive radius. So there exists some w0 and some epsilon, such that the ball w0 epsilon does not intersect the image. Once you have that, you shift omega 0 to 0, you take 1 over z, and you get a holomorphic function from omega into the ball of radius 1 over epsilon. And then you scale, so you get some injection between omega and the unit disk. Okay? This is completely standard. There's no big issue here from the mathematical point of view. It's just to have everything on the board and talk about what you want to do to formalize every step. Okay, so this is the first step. Okay, second step is you want to maximize f. So step 2, you will look at this function, the map from that takes f and gives f prime of z0. You define it on f, and you want to say that this is a continuous function if you equip f with the natural topology. So f is equipped with, so the natural topology is the topology of uniform convergence on compact sets. So it's locally uniform convergence. So then you know that if you have a sequence of holomorphic functions that converge in this topology, then f prime also converges. That's the Weierstrass theorem. And this tells you that this map here is continuous on f. So this map is continuous from f to r plus. Okay, and the second thing is that these functions, f, on this big set, they are uniformly bounded, and Montel's theorem tells you that they are equicontinuous. And then you have the Ascoli theorem saying that f is actually a compact set. So you have a continuous function on a compact collection of functions. You can maximize, and you can give one particular function which realizes the maximum. So there is a function f such that f prime of z0 is maximum. Okay, so that was step 2. You can extract the maximizer of this particular observable, and you get one particular function. Okay, in step 3, what you want to do is to show that this particular function f is actually a conformal map between omega and the unit disk. So f goes. So it is an element of f, so it's holomorphic. What you need is that this is a bijection, and that is so it's into and it's onto. So why is it onto? here the usual trick is you assume that you take a function which is injective and not onto, and out of that you build a function that has a bigger value for the derivative. So here is one way to do it. Again, this is very classical, but I want to have the whole argument to see where the formalization is going to be tricky. So this is omega. Take a function g, which maps into the unit disk, but you assume that there is a point that is not in the image. So the image is something like that. And then you do a similar trick as this one. You map this to the origin by a Möbius map. Then you apply the square root. And you say that square root has a big derivative, and so you make a calculation, and it proves that once you unfold everything by square root, you get somewhere a derivative that is bigger. So essentially, it's a calculation. There's this h in F such that h prime of z0 is strictly bigger than g prime of z0. So in particular, well, if you take a function that maximizes the derivative, it has to be onto. And then why is it into? Well, then you have Hervé's theorem saying that if you have a collection of homomorphic functions that are into and that converges locally, then the limit is either injective or constant. Well, it cannot be constant because f prime is not 0, so it has to be injective. So this is Hervé's. Okay, so we have all the pieces. This is essentially a complete proof. And let's summarize what we need. We need essentially the whole undergrad course of complex analysis to be able to justify all the steps. Okay? So the plan is go over all the prerequisites, go over the argument, and see what we can do in Lean to implement this proof. So here is a restatement of the theorem. In Lean. So I just copied and pasted the informal statement here. And this is the statement in Lean. So it says you take a domain U, it's open, it's connected, it's not, so univ is the whole space. And you assume that U has primitives in the sense that every holomorphic function on U has a primitive which is holomorphic. And for those who looked at these kind of things before, this is where I'm cheating. This is the thing that replaces the simple connectedness assumption. Okay, then given these assumptions, there is a function which is differentiable in the complex sense on U. It's injective on U, and the image of U is the open ball centered at 0 and radius 1. So this is the statement, and this is what I proved. So it's not the full Riemann mapping theorem, because this assumption H4 here is not exactly the same as in the theorem. And I will come back to this in the third part of the talk. Okay, so what did we need? Yeah.
What did you prove that U is not empty?
Where did I use that U is not empty? Connected implies that it's non-empty.
Connected implies non-empty?
Yeah. The empty set is pre-connected, but it's not connected.
As you may
yeah.
know.
So it's not written explicitly, but it is there in this assumption. Yeah, good question. I'm supposed to repeat the questions. The question was, where does it say that it's non-empty? It's stated here. So this is essentially the list of basic theorems of complex analysis that we needed. That we need something about isolated zeros of analytic functions and the open mapping theorem, and these come as a package, like the way to prove the open mapping theorem. One of the ways, the one I know, uses the isolated zeros. You need Möbius transformations of a unit disk to be able to move points in the image and manipulate the thing in the second step. You need something about uniform convergence of functions on compacts and the fact that the derivative converges. You need something about normal families and uniformly bounded collections of holomorphic functions and the fact that they are equicontinuous and relatively compact. And you need something about the injectivity of the limit. And okay, so let's look at what this looks like in Lean. And essentially, that's what I had to formalize in order to have the basic blocks for the proof. The big gap, the one thing that is missing, is the link between existence of primitives and simple connectivity of the domain. So this is kind of written, but not quite as well as we would like. So there is still ongoing work on that and the hypothesis and the way to construct that, and I will come back to that in the end. So it would be central in statements of the Riemann mapping theorem if you wanted the full statement. And it's also something that is occurring in the project, so the PNT Plus project is the prime number theorem and more project, which is currently ongoing. It's driven by Terence Tao. And okay, so I've been involved in this project as well and trying to use what I did in complex analysis to help in some of the steps here. So I will go back to this maybe a little bit in the end. Okay, so the point is to show you what these statements look in Lean. And so this is the principle of isolated zeros, and there are a few versions. So I know that there will be a tutorial on analysis on Thursday, I think, but I will kind of have to talk about filters just to explain the statements here. But you should not be traumatized by filters. Because you don't see them, essentially. Can you see the filters? So filters is this F here, right? But it means eventually. So this is the local version of isolated zeros. So you take a function which is analytic at a point, and then this is an OR, so we are in one of two cases. First case is for every z in a neighborhood of z0, and for every exponent f means for every z close enough, then fz is equal to 0. So this means f is locally equal to 0 in a neighborhood of z0. Or for every f in this neighborhood, so close to z0 but not equal to z0, fz is not equal to 0. So this is exactly the translation of the statement of isolated zero. Either 0 is isolated or locally the function is 0. Okay, I'm not going to show you proofs of these, but the argument in Lean is the same as in the math textbook. You say that the function is analytic, so it's a sum of a series, and you would look at the first non-zero coefficient. If it exists, then the function is not 0 locally. If it does not exist, then it's 0 in the whole disk of convergence. So the proof is exactly the same. Okay, this is a more global version. You take a function that is analytic on a domain. The domain is pre-connected. You take a point in U. So in particular, U is not empty because it has Z0 in it. And you suppose that around Z0, there is an accumulation point of zeros. So this is the exists exponent f. This means that you can find a point satisfying this assumption arbitrarily close but different to Z0. So this is exactly saying that there is an accumulation point of zeros. And the conclusion is that under this hypothesis, the function is identically 0 on U. Okay, again, this is a very standard math result, and the proof in Lean is the same as the proof on the blackboard. You look at the collection of points where the function is 0, and you say that it's both open and closed. It's open because of that. It's closed. Or it's not 0, sorry. And you use connectivity to show that either it's everywhere or it's discrete. Okay, and out the corollary, the identity principle, if you have two functions that coincide on a set that has an accumulation point, and they are both analytic, then they are the same function. Okay, so this is just mainstream mathematics, and it's something that you can just formalize. You take the textbook and you map everything from the left to the right, and it gives you essentially the Lean proof.
Excuse me?
Yeah.
What is your hypothesis on K, connected space K? Well, K is a complex numbers? Or
Yeah, here K is.
maybe
Yeah, so this is slightly more general, so you can define analytic functions on manifolds and something like that, so it's more general. You need connectivity so that, otherwise you need to look at a connected component. But you should read that it's a domain in C that is connected to match it. So, yeah. Yes?
K is an non-trivially normed field.
Yeah, but it could be Q, and for Q there's a problem. So you can read C, and the main content is that it's C, from my point of view. Okay, second thing, you need the open mapping theorem. So again, this is what it looks like in Lean. It says that, so the second version, you take an analytic function on a pre-connected U, and you are in one of two cases. The first one is G is constant, so there is a W such that for every Z, GZ is equal to W. It says that G is constant. Or it's open. It's an open mapping in the sense that if you take an open subset of U, then the image is also open. The way it's written here is slightly more exotic. It's a local version. So the local version tells you that if you take an analytic function at Z0, then either it's constant in a neighborhood, or it's locally an open map in the sense that it takes any neighborhood to a neighborhood. And when you learn more about filters, you will know why this is an inequality between filters. This really tells you that the image of a neighborhood of Z0 is a neighborhood of GZ0. So again, the argument is the same as you use the power series and you say that it's going to work. Okay, so still looking at the different bits that we need in the argument. This is about the local limits of holomorphic functions. So F is a collection of holomorphic functions. So it goes from some index space to functions. And for every n in the index space, you assume that Fn is holomorphic on U. And again, U is an open set. And you assume that you have local uniform convergence to some function f, then the limit is also holomorphic, and the derivative, which is here, converges to the derivative of f. Okay, this works, and again, it's here you need to be a little bit careful, because if you want to show that the derivative converges, you start to need something like Cauchy's formula to write the derivative as a function in terms of the function. So you need some kind of contour integral. And contour integrals, they are, as I said, it's not well, it's not really satisfactory the way we have them. Here you can get by with only looking at circle integrals, and there's huge support, API support for circle integrals in MATLAB already. So what you do is you write the derivative here as a circle integral, and you say that if you converge uniformly on the circle, then the limit is also a circle integral, and it works. Okay, then you need the compactness of the collection of functions. And here is a place where I was very lucky because Anatole did most of the work. So Anatole is here, thanks. And so this is the statement where you don't see the whole work of Anatole, and then I'm going to tell you to show you the second version. So okay, you take a collection of functions. So f goes from some index space to functions from C to C, and you take U, which is a set. And you define a uniformly bounded collection of functions by saying that for every k, which is a compact subset of U, there is a compact Q such that all these functions map k into Q. So this is a uniform bound on the functions, uniformly on compacts. And the theorem tells you that if you take such a collection, then the range of f as a collection of maps is totally bound. So how do you do that in Lean? This is just to show that you can make something a little bit more expressive than using quantifiers and such. So the big input is this big C of U here, which is the set of functions, well, the type of functions from C to C. But this notation tells you that it's equipped with the topology of uniform convergence on compact sets. So you're not assuming the functions are themselves continuous, but you put the convergence of the topology of uniform convergence on the compacts on this collection. Okay, and then you define H of U, that's the set of functions in C that are differentiable on U. And it's a subset of this, so it inherits the topology, so it's automatically equipped with the topology of local uniform convergence. And M of U is this that I called F here, except you don't want them to be into, so it's the holomorphic functions that map U inside the closed ball of center 0 and radius 1. Okay, and the main statement is that this set here is a compact set. So this is the Arzela-Ascoli, one version of the Arzela-Ascoli theorem. So once you have that, then you can extract converging subsequences. Okay, one last bit here is the Hurwitz theorem. So here are two statements that essentially are enough to implement the third step. So you take an open set that is connected. You take F, which is a collection of holomorphic functions on U. Here, for technical reasons, they are only holomorphic for n large enough, but it's the same. And you assume that they don't vanish. So for every n and every z in U, f and z is not equal to 0. And you assume that they converge locally uniformly. And then, well, we are in one of two cases. Either f itself doesn't vanish, or f is identically 0. So again, how do you prove that? Well, you say that you can count the number of zeros of a function as a contour integral. It's essentially the contour integral of f prime over f. And this depends continuously on the function, and it's a discrete valued function. So if it is non-zero for every n, then it has to be non-zero in the limit, unless the integral is not well defined, and that means that f is 0. So again, from the point of view of a standard mathematician, this is just an argument about contour integrals. If you don't have the theory of contour integrals in high enough generality, you need to be a little bit careful, and you can get by using circle integrals again. So you can essentially make a local version of that and show that fz is not 0 by taking a contour around z and applying what you know about circle integrals. And again, I will come back to this way of cheating in the next part. Okay, so the corollary of that is the injectivity of the limit. So again, you take a sequence of functions that converges locally uniformly, and you assume that they are all injective on U, and then the limit is either constant or injective. And again, this is the same argument. You assume that it's not injective, so then there is a point that it takes twice, and you look at the difference, and you get something that has value 0, and it shouldn't. So this is just to convince you that you can just write the statements of standard mathematical analysis results in Lean, and the proof is essentially the same. Okay, now for the part that is not really satisfactory, which is there are many places in all this story where you want to have a nice notion of contour integrals. You want that to count the zeros, you want that to have Cauchy formula on the general contour, you want something like that to have existence of primitives. Once you have primitives, you have square roots, so this part is okay, but if you want to have primitives, the natural way to do it is to integrate a function on a contour and say that the increment of the integral gives you a primitive. And the point is that there is no nice way to have an integral for any kind of function on any reasonable path. So you need to make a choice. And this is where the thing is kind of still in progress, and it has not really progressed recently because it's not clear what to do. So what do you do if you don't have a general theory of contour integrals? So as I said, the first option is you cheat. What does it mean? Well, you use only specific shapes. So here is one example. In all the theorems about counting zeros and all that, what you can do is, if you want information locally on f at a point, you look at circle integrals on circles around this point. And then you use explicit power series, and power series work very well for that. And the circle integral can be written in terms of the series. And everything works explicitly, and it works very well. But the moment you want to have a point which is not at the center, it's a little bit complicated. It can be done, but you need computation, and you don't want to compute. I mean, it adds pain that should not be there. Something else, it's very useful to have something like the residue formula. So you take a meromorphic function, and you have a contour, and you want to compute the contour in terms of the sum of the residues of the function. And a priori, you are not always able to choose as a contour the circle. And that's typically what happens if you want to use complex analysis to do analytic number theory. You have contours that are constrained to be in half spaces, and they cannot be nice large circles where you can do what you want. So in the PNT project, essentially the idea comes from Alex Kontorovich. He uses rectangular integrals. So why is that useful? So assume you want to prove the residue theorem for a rectangular domain. So you have a function here. You know that it's holomorphic except at one point, and at this point you get a singularity like 1 over z. And you want to compute the contour integral in this domain. You don't want to do homotopy of rectangles because it's not natural. It doesn't fit what you want to do. So what do you do? What you do is this. You slice the rectangle into sub-rectangles. These are rectangles where the function is holomorphic, so the integral vanishes. And the integral on the small square here, it's equal to the residue plus a little bit of error term because it's very small and you can approximate the function. Okay, it works, but that's the only advantage of this method. Right? It's not natural at all. It's painful, and if you imagine how to do that in Lean, without the automation, you have to sum 9 terms and prove cancellation piece by piece. It's, I mean, he did it, but yeah, it's not optimal. You can add assumptions on the domain. So if you want to prove the Riemann mapping theorem on some natural class of domains, you can add some assumptions like convexity. If you have convexity of the domain and you want to compute a primitive, there's a natural collection of contours. You can just take straight lines, and they are contained in the domain. So if your domain is star-like around a point, there's a natural definition of something that should be a primitive. And this can be rewritten as integrals on some real intervals. And then it's a parametric integral. You can differentiate in the parameter and prove that you actually get a primitive of your function. So again, it works, but it doesn't feel like it's the right thing to do. Right? You don't want to have parametric integrals and differentiate in the parameter if you have a nice theory of complex analysis. I mean, the whole point of complex analysis is that you don't want to do computations like this. So this can be done. So I have a version of that. That's holomorphic functions on the star-like domain have a primitive. But it's not really satisfactory. Okay, so option 2 is maybe the most natural one. You limit the collection of contours that you want to consider. Instead of general continuous contours, which you would need if you want to do simple connectivity, you limit to piecewise C1 contours. Well, then everything works well. You can define the contour integral as the integral of f times gamma prime along the contour. And it works. It's well defined. You get a nice definition of contour integrals. But again, what you want to do is homotopy of paths and homotopy of piecewise C1 contours. I mean, I don't know if you want to do that in Lean, but I don't. And besides, if you want to build an explicit contour and go from one place to the other one, it's a little bit messy. It's a bit less messy if you add the assumption that the contour has a differential that vanishes at the end, because then it's C1 everywhere and you can glue them together and it's a little bit nicer. You can take corners. But again, it's not optimal. And option 3, if you want to integrate functions along continuous paths, it's not possible to do that in a nice way for arbitrary functions, so you can restrict the functions. You can restrict to holomorphic functions. And here the point is that if you have a holomorphic function, then locally it's a holomorphic function on a convex set, so locally it has a primitive, and so you can build local primitives and put them together. And it kind of works, again. So there are two ways to do that are natural. Either the first one is you want to approximate by C1 contours. So what you do is you take your continuous contour, you take an approximation which is C1 and contained in your domain. And this is not so difficult to do. You approximate by C1 contour. You define the derivative, the integral along the C1 contour using integral of f times gamma prime. And you show that this is invariant by deformation among C1 contours. So again, this is a computation using parametric integrals if you want, and using the holomorphicity of the function. It works, but again, it's a little bit messy to do it properly. And then once you have that for C1 contour, you define the integral in a continuous contour as the common value for all the functions in the neighborhood. Okay, so this will extend contour integrals to continuous functions, but it is not very explicit. Right? It's defining it as a limit, and working with limits, it's not very comfortable. So probably the right approach is to do it directly by path lifting. So essentially what you want to do if you want to compute integral of a holomorphic function along a contour, a continuous contour, is you look at all the functions on your domain and you make a covering structure on it by saying that, okay, the neighborhoods of a point are locally functions that are local primitives of f. You build a topology out of that, you show that this is a covering of your domain, and then if you want to integrate the function along the path, you just lift that through the covering and it gives you a contour on the top. So this gives you the value of the primitive just by lifting. And then you do general topology. You say that, okay, once you have it as path lifting, if you do homotopy lifting, you get that it is invariant by homotopy. And this is probably the right approach. This is the way that you get the nice topological features that you need if you want to do contour pooling and if you want to do the usual thing that you do in complex analysis. So this is probably the right thing to do, but it's kind of involved. So path lifting, a few people did path lifting in coverings. So there are a few versions floating around. As far as I know, there is none in MathLib yet, but maybe eventually there will be one. And homotopy lifting, I don't think this has been done yet, but it's probably the right thing to do.
I think Julian too.
He had a version of the uniqueness. Maybe he did the existence, but I don't think he published it. Yeah, no, he's worked on that, and I think he did the uniqueness. Okay, so as I said, this is my first talk in Lean, and I went quicker than I thought I would. So this is all I had to tell you today. So please, if you want to contribute and build one of these bullet points, come to me. I would be very interested in talking to you. And thanks.
Are there any questions for Vincent?
Thanks for the talk. And you said several times the proof is the same as at the Blackboard. And did you really feel it was the same as the Blackboard version?
Yeah, almost.
Okay, this is very good news. We usually suffer a lot. So
I mean, it was kind of surprising, but it's very close. I mean, even the argument usually when you want to prove the open mapping theorem is you say, okay, you take a function in the image, you take a small circle, it doesn't take this value, and you look at the distance, and you get it.
This looks painful to formalize, and it
no,
wasn't.
this is you formalize line by line, and it works. And I can show you the proof. It's exactly, you take the book proof, and you formalize it. And
nice.
And the only place I had to fight was coercions. Between non-negative reals and reals, because the distance and the non-negative distance, they don't want to talk
I guess
to each other.
we all know that feeling.
Yes. And then you ask Sébastien Guazel, and he says, what do you mean? It's just you do that. And he has an incantation, and it works. And we all know that feeling as well. But yeah, mostly it was not painful. I cannot say the same about real analysis. That's painful.
Okay, thanks.
So real analysis is harder to formalize?
I mean, bounds on real integrals, if you want to change one subterm somewhere to have a bound and get a bound on the big integral and quantitative things. I mean, mathematically it's more basic, but technically in Lean it's more painful, in my experience. Maybe I've been doing it wrong. I don't know.
Thank you for the talk. So I have two questions regarding, like, I guess, option one. So I guess the first question is, like, why do you need rectangular integrals when you can do, like, like circle integrals and kind of zoom into the.
Yeah, so you can. And this is done in MATLib. The reason is sometimes you want a big contour to use the asymptotic behavior of a function, but you want to live in a half space. And there's a pole close to the boundary. So you cannot make a big circle that is centered at the singularity because it goes out of the domain. So either you take a big circle, but it sneaks in between, and then you lose all the asymptotics that you want.
Right.
Or you need to change the domain to take a rectangle, and here the point can be close to the boundary.
Right. Right.
It's not deep reasons. It's just, I mean, you need to minimize the total amount of pain, so you have to sprinkle the pain when you want.
And we do have, like, say, like, how do I say this? Like, if your contour is not made up of a very specific shape, but it's like piecewise made up of specific shapes. So you can like the top half is a circle, but the bottom half is a rectangle or something.
Yeah, then you have to mix the definitions, or you say that piecewise continuous is just continuous. It's what you want to do. But
okay.
Yeah, piecewise C1. It's kind of workable, but it's. I mean, piecewise anything. If you want to do it in a family, it's not nice.
Thank you.
Have you had a look at how they did general contour integrals in Isabelle with this winding number stuff?
So I looked in Isabelle, and everything I found was about acceptable contours which were piecewise C1. Maybe I didn't look where I should have, but I did not find more generality than that.
Okay, I don't know. I remember that there was some stuff in Isabelle that we didn't have in Lean.
There is a formalizing of the Riemann mapping theorem with essentially the same proof.
Yes.
The assumption is existence of the square root and not existence of primitives, but it's exactly the same proof. And it follows the same steps, and everything I found was piecewise C1 contours used everywhere.
Okay, I'll check what I remember, but yeah, thank you.
Okay, I have a question too, the more lean related. Can you give us an idea of how big the project was in the end? How much time you spent on it? How many lines of code or files did you have to create, or PR you have to add?
Yeah, so about half is in Mathlib now, and it's about maybe 2,000 lines, plus what Anatole did, which I did not count. It's reasonable.
And how long did that take?
No, that is not reasonable. Yeah, you should never ask somebody how much time they spent on the formalizing project, right? It's not polite.
Okay.
Yeah, no. I started, yeah, no offense, it's just a joking, but I started 3 years ago. And I had to do all that. I showed you all the list of bullet points, and I mean, yeah, a few months full time, I guess.
So let's thank the speaker again.